Section 9.8, resonance and formal charge. Some structures have more than one valid Lewis structure. So let's look at ozone, which is O3. So drawing that, we've got 3 oxygens. So they're going to have to go in a row. And then how many valence electrons are going to be in this Lewis structure? 18, right? Each oxygen has 6, so 3 times 6 is 18. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18. Not quite enough to make everybody happy. We need to do a little more sharing. And so we'll take one of these lone pairs off the middle and put a bond over there instead, 2, 4, 6, 8, 2, 4, 6, 8. So now everybody's happy. Why does the oxygen on this side get the double bond and not the oxygen on that side? But what if we put the lone pairs over here and put the double bond over there? Would that be okay? I'm going to draw that down here. Is that an okay Lewis structure too? Sure it is. So there's 2 valid Lewis structures. How do we know which one is correct? Well, it turns out that neither of them is correct. Ozone actually exists as an average of these 2 Lewis structures. There's various scientific evidence that shows that these bonds are actually equal in length, which tells us that one is not double and one single, but that they're both kind of a 1.5 bond. They're also equal in strength. Well, Lewis theory doesn't have a great way for showing that. And so the best we can do, which, you know, I've got all this writing in here, so, but just bear with me, is we put a double-headed arrow between the 2 structures, and we say the actual structure is an average of these. Now, sometimes students get the idea that it's actually resonating, bouncing back and forth, but that's not the case. It's not one or the other going back and forth. It is a combination of both.
Is that something that's with oxygen?
It's not just with oxygen, not just with ozone. We see it with lots of different things.
What do we use to memorize that?
Well, we'll see. We'll get to that.
And you always draw both of them out?
You draw all of them with double-headed arrows, and sometimes there's more than 2. There could be 3 or 4. It's fun. So the actual structure is a resonance hybrid, just like if you took a German Shepherd and a white lab, and one's a boy, one's a girl, and they have a puppy. The puppy is going to look like a combination of the 2 parents, right? You don't see this dog, one day it looks like a lab, and one day it looks like a German Shepherd, right? It always looks the same, and it kind of looks like the father, and it kind of looks like my mother. I should show you pictures of my kid. They're resonance hybrids of my husband and myself. They're half samurai and half Viking. It's a good genetic diversity. They're vigorous, right? There's no inbreeding there. And so that's what happens with ozone. We see these 2 different possible structures, but what it really is something that's a combination of them. And each of these oxygen-oxygen bonds is actually 1.5 bond. And that's a little hard to understand just based on the Lewis model. And we'll see that when you get into more complicated bonding models, that makes a little more sense. The Lewis model always shows electrons as being localized, meaning that the electrons have to be associated with a single atom or between 2 atoms. But in fact, atoms are often delocalized over several atoms or bonds. And this causes the energy to be lower. And so it's a resonance stabilization. And this explains the stability of some molecules that would otherwise not seem to be as stable as they actually are. So let's draw a Lewis structure for the nitrite ion and see if we can identify what the the resonance structures are. So NO2, the first thing we're going to do is we're going to make a skeleton, not with the marker, but with the pen. And so we'll make a skeleton here. We'll put the nitrogen in the middle and the oxygen on the sides, because things usually tend to be symmetrical. And like on an exam question, if it's not going to be symmetrical like that, we'll give you some indication, tell you which one's in the middle or something. And then we have to have at least one single bond between these. And then we have to figure out how many valence electrons do we have. Well, there's 2 oxygens, they each have 6. And then there's 5 for the nitrogen. The negative charge, do we add 1 or subtract 1? Add 1. So this ends up being 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. That looks a lot like the ozone one, doesn't it? Because in terms of the valence electrons, it's the same. It's 3 atoms bonded together and a total of 18 electrons. So we're going to end up with the same thing where we have 1 double bond and 1 single bond. So the way we identify that there are resonance structures for this is we see that here's a double bond between nitrogen and oxygen. Here's another nitrogen and oxygen. This oxygen is no different than that oxygen, but one gets the double bond and one gets the single bond. It's a little bit like, the kids. You have 2 kids and you give one a Game Boy and you give one a puzzle. And they're like, why? Why does he get the fun thing? Question?
Does the nitrogen have to have 8 electrons? You can't put the other 2 in the other oxygen?
We're sticking with things that obey the octet rule here.
Okay.
There are things that violate that, but we'll worry about those later. So right now, everybody has to have 8 valence electrons. And we're going to learn very shortly about something called formal charge, which helps us decide even better where to put the electrons. But here, putting the double bond here or here is exactly equivalent, right? Does everybody see that? So we can also draw this over here and give the double bond to the other oxygen. And exactly where you draw those lone pairs doesn't really matter, as long as you've got 8. And I didn't leave enough space because I didn't see what I was doing. But there's the double-headed arrow, indicating that those are resonance structures. What's missing from the resonance structures? Brackets and a charge. By the way, mastering chemistry can't do brackets. So please do not text me and ask me how to do brackets. Mastering chemistry can't do brackets. Okay, I don't know why, but anyway. So those are the resonance structures. Any questions? This is different than just flipping a molecule. So cyanide ion looks like this. And you could also draw it with the nitrogen over here and the carbon on this side. But that's actually the same thing, right? You just drew it backwards. And on the surface, this might look to you like the same thing drawn backwards. But there are 2 different oxygens. And we can identify which one is which by putting in 2 different isotopes of oxygen, and we can figure out which is which. You can essentially tag one that way. And so we can tell which is which. This is just drawing them in different arrangements, and so that is not resonance. Okay? This brings us to a concept called formal charge. Formal charges are fictitious. Okay? This is a thing that we made up to help us predict the behavior of atoms and electrons in the bond. So the formal charge of an atom in a Lewis structure is the charge it would have if all the bonding electrons were shared equally between the bonded atoms. And then any non-bonding electrons belong to the atom that they're on. So they give you this formula that the formal charge is the number of valence electrons minus the total of non-bonding electrons plus half the bonding electrons. And if that works for you, great. That just doesn't really work for me very well. So I'm going to show you what works for me. It's important to remember we're not looking at electronegativity at all. We recognize that many of these electron pairs, the bonding pairs, are not shared equally. But when we're computing formal charge, we pretend that they're shared equally. It's basically the difference between the number of valence electrons that that atom brought to the molecule and the number that it owns in the Lewis structure. And sometimes it gets a little bit out of whack. So let's look at our rules here. The sum of all formal charges in a neutral molecule must be 0. Sum of formal charges in an ion has to equal the charge on the ion. Small formal charges are better. Okay? Small or 0. Silly. 0 is the smallest, right? 0 is smaller than 1. That's what the book says. When formal charges cannot be avoided, negative formal charge should reside on the most electronegative element. So if you can't arrange it to avoid formal charges, we want to put the negative formal charge on the more electronegative element, because that's the one that's more attractive to electrons, and so it's better able to handle an extra electron or two. So let's look at cyanic acid, hydrocyanic acid. It's not real obvious what this table is doing because I just had to look at it for a second. The structures are hiding right there, but I'm going to draw them so that we can see them a little better. So on the left here, this is structure A with a lone pair there. And on the right, we're going to put N in the middle and a C on the outside. And we're going to compute the formal charges for each atom in each of these structures and decide which one is going to be better. So let's look at hydrogen. So the way I think about this is I'm going to take a circle around hydrogen. I'm going to include any lone pairs he has, and he gets half the bond. It's a little bit like, okay, these guys are getting a divorce, and these are the children that they share between them, and they're going to just divide them. You get one, I get one. And here's carbon and nitrogen, and they've got 6 children between them, so carbon's going to take 3 and nitrogen's going to take 3. But these two over here definitely belong to nitrogen, because those were from a previous relationship, right? These, someone really needs to speak with these elements. Good grief. Just creating huge messes for themselves. It happens, though. Okay, so this makes more sense to me. We're just dividing things up. You take all the bonding electrons and you split them equally between the two atoms that they're being shared between. So you cut them in half. So this is 1, 2, 3 for carbon and 1 over here. So here carbon has 4 electrons that it owns. And how many did it bring? How many valence electron does carbon, the atom, have? 4. So it has 4, and here it owns 4, and so its formal charge is 0. How many does hydrogen own in this structure? 1. And how many did it bring? 1. So 1 minus 1 is 0. We're doing well so far. How many does nitrogen have here? 1, 2, 3, 4, 5. How many did it bring to the molecule?
5.
5. 5 minus 5 is 0. 0 formal charges. This is good. Then we look at the other one. So here's something to help you out. Hydrogen, pretty much always formal charge of 0, because he makes one bond and he doesn't have any lone pairs. So we don't even need to look at the hydrogen. But let's look at nitrogen. We'll stick with green for nitrogen. So we know that nitrogen has 5 valence electrons, and how many does it own in this structure? It has 4. So 5 minus 4 is 1. And here's carbon. Carbon has 4 electrons by itself. And in this structure, it has how many? 5. So 4 minus 5 is minus 1. And then, of course, hydrogen is almost always 0. So this structure, everybody has a 0 formal charge. And over here, carbon has a minus 1 formal charge. Nitrogen has a plus 1 formal charge. Who's more electronegative, nitrogen or carbon? Who's closer to fluorine? Nitrogen. Nitrogen is more electronegative. So here we have the more electronegative element having the positive formal charge and a less electronegative element having a negative formal charge. That's not a good situation. So this, structure A, is going to be the best. This is what helps us to determine which of these possible Lewis structures is the actual one. Any questions?
Isn't carbon normally the central element?
Carbon frequently is the central element. And there's another thing kind of going on here too. If we look at the electrons, the valence electrons and how they're arranged, we find that carbon usually forms 4 bonds, nitrogen usually forms 3 bonds, hydrogen always forms 1 bond. And so here we see that nitrogen has 4 bonds, and that's not normal for nitrogen, and carbon only has 3 bonds, and that's not normal for carbon. And so that can give us a tip-off too. And that you can predict from the periodic table. The group 7 elements form 1 bond, group 6 forms 2, group 5 forms 3, and group 4 forms 4. So it's the same pattern as the charges of the anions, but it's a number of bonds instead of number of electrons being gained. So let's assign formal charges to each atom in the resonance forms of N2O. Which resonance form is likely to contribute most to the correct structure? Well, let's look at N2O. We could put O in the middle. And we've got 5 valence electrons for each nitrogen. So that's 10, plus 6 for oxygen, so 16 electrons. So we've got 2, 4, 6, 8, 10, 12, 14, 16. So that's not going to work out. So we can move those to become a bond, and we can move these to become a bond. And when I do that, I'm not gaining or losing electrons. I still have 16. 2, 4, 6, 8, 10, 12, 14, 16. Are all of these atoms happy? Do they have octets? Yes, they do. Is there any way we could draw this that that's different, that they would still have octets? This is where you can get a little creative. What if we gave a triple bond to one nitrogen and a single bond to the other? Same number of electrons. What if we put the oxygen in the middle? No, we have the oxygen in the middle. What if we don't put the oxygen in the middle? Sorry. What are you talking about? I do that just to trick you. Well, we're going to need either 2 double bonds or a triple and a single. So let's just go ahead and do 2 double bonds. And then this guy's going to need 2 lone pairs, and this guy's going to need 2 lone pairs. Or we could do the triple like that. Two, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Did I miss anything? Did I miss a possibility?
On the top right, can you do it to the other side?
Yeah, this one, we could give the triple bond over here and the lone pairs over there. The formal charges will end up being the same that way. And we can't make little triangles or anything, not with these guys. Okay, so let's look at formal charges. Let's see if we can do it. Well, actually, I'll draw circles on the first one, and then we'll try and do it without drawing circles. So here, for this nitrogen, we know that nitrogen has 5 valence electrons. How many does it own in this circle? 6. So 5 minus 6, this has a -1 formal charge, right? And we'll do oxygen in orange. Oxygen brought 6 electrons in, and how many does it own in the structure? 4. So 6 minus 4 is +2. And this nitrogen over here is the same situation as the first one, isn't it? So this is also -1. Are those great formal charges? No. At least we have the negative ones on the more electronegative element. No, wait, we don't. Oxygen. I was thinking carbon. No, so this one's just totally screwed up. Okay, so let's look at this nitrogen. Nitrogen brings 5. How many does it own in this structure? 5. So what's its formal charge? 0. How about this oxygen in the middle? It brought 6, it owns 4, so it has a formal charge of 2. And this nitrogen brought 5, owns 7, so this is -2. And look, this is a neutral molecule, right? So -1 plus 2 plus -1 adds up to 0. Here, 0 plus 2 minus 2 adds up to 0. If they don't add up to the same charge as on the molecular ion, then you screwed up somewhere. Is everybody getting how I'm doing this? Okay, because I don't want to bore you, but I don't want to lose anybody either. So what's the formal charge on this nitrogen? Well, it's got 6 electrons, but what's the formal charge? -1. It came with 5, it owns 6, it's -1. How about this one in the middle? +1. And this oxygen? 0. So that's the lowest set of formal charges we've had yet, right? And then let's look at this guy. So this nitrogen, how many? That one's 0. And this one in the middle? +1. And the oxygen? -1. So the top 2 we can rule out because they have formal charges, at least one that's a 2. The ones in the bottom have lower formal charges. That tells us they're better. And then we have to choose between these 2. Well, we want to have the negative charge on the more electronegative element. Oxygen's more electronegative than nitrogen. And so this is going to be the preferred structure. This is a resonance form of this. Can you see that? It's not real obvious. Those are resonance structures. Okay, let's do diazomethane. You are not expected to know what that is. They gave you the formula. Let's do orange for a while. So CH2N2. Well, we shouldn't write with that one to start out with. We can hook these guys together in different ways. We could do that. We could do something like that. Now the possibilities just become almost endless. We put the H on the end. There's CNN. You put the H here and an H here. No, I just thought of one more. We could do that too, huh? That's nice and symmetrical.
So all the exam would be given like 4 options and you have to figure out, or we have to solve
You would be given, in like a multiple choice question, there'd probably be 4 or 5 Lewis structures, or maybe just, well, it would probably be a Lewis structure. And you would have to decide which is the most likely one based on formal charges. But no, I probably wouldn't ask you to come up with these. This is fun in one way, but then in another way, it's just really not very fun. Okay. Nitrogen and nitrogen each have 5, so that's 10, plus 4 for the carbon is 12, 13, 14 electrons. 2, 4, 6, 8, 10, 12, 14. So what can we do there? Can we make that one satisfy the octet rule? Is it possible? No. We don't have enough electrons to give the nitrogens lone pairs to make up their octets. But if we start sharing more, if I take this one and put it in here, then carbon has too many electrons. Carbon cannot violate the octet rule. So that one is not going to work. Well, let's look at this one. I said I should write this down. We've got 16, right? 16 valence electrons? Because I'm going to forget. 2, 4, 6, 8, 10, 12, 14, 16. Okay. But now we can do some double bonding. We can take this guy and put him in here. And now carbon's happy. And this nitrogen in the middle's happy. This guy's not. But we've got this lone pair here we could move over. We could do that. Does that satisfy the octet rule? It does. Okay, let's figure out what the formal charges are. The hydrogens we don't even need to worry about. Carbon brings 4 electrons. How many does it own? 4. So that's got a formal charge of 0. Nitrogen brings 5 electrons to the molecule. How many does it own? 4. So 5 minus 4, this is plus 1. And this nitrogen brought 5 and owns how many? 6. So the formal charge is minus 1. Okay. Well, that's not horrible. Let's see how these others work out. So down here, 2, 4, 6, 8, 10, 12, 14, 16. Well, we could take this lone pair and move it. That's not what I meant to do. I meant to do that. The carbon's happy. I can't share this with the carbon because then the carbon will have too many electrons. I can't share this with the carbon. I can't share that with the hydrogen. We're kind of stuck there, huh? That one's not going to work out. We can't do the octet rule. He's out of the running. Always nice when that happens. Let's go to this guy. 2, 4, 6, 8, 10, 12, 14, 16. Time for some multiple bonds. We'll take this guy and put him in there. Now, nitrogen's happy, carbon's happy. This nitrogen's still not so happy. So we'll take this lone pair from carbon and go over here. Does that satisfy the octet rule? Yeah, it does. Okay, formal charges. This nitrogen, what's its formal charge? 0. It owns 5. It brought 5. The difference is 0. This carbon, what's its formal charge? 0. How about this nitrogen? 0. It's got 2, 3, 4, 5. Half of each bond plus all the lone pairs. 0 formal charges on everybody. That's good. That's good. I guess we should finish that last one. I'm really not feeling it, but well, we could. Yeah, this isn't going to work at all, is it? Because if I put 3 bonds in there, this nitrogen has too many, and if I put a multiple bond in here, that nitrogen still has too many, and so that one's just plain not going to work either. So the winner is this guy. The structure with the lowest formal charges wins. If there's a tie, the structure with the negative charge on the more electronegative element wins. Any questions?
You can also rewrite that one, can't you? You just flip the 2 pairs.
If we flip anything, it's still actually the same molecule. Yeah. So, I mean, these lone pairs could be drawn on the bottom. You could draw this nitrogen over here and that nitrogen over there, but nobody would be able to tell that you did that. Right? You could put these lone pairs on top, but it's all the same. Any questions? What is the importance of this? Well, that's an excellent question. The importance of this is it helps us to predict which structures actually exist, and it's very useful for predicting the best Lewis structure. And what we'll see is when you have resonance forms, sometimes they don't have the same formal charges, and so you can predict that this one one structure has more of an influence on the resonance hybrid. Like if you look at my children, the children that belong to me and my husband, right? He's Japanese, I'm of Swedish descent. Who do they look more like? They look much more like my husband, right? He had more genetic influence on their appearance than I did.
Doesn't that suck? Since you're like, you're
No.
the one that holds them for like 9 months.
Well, I know.
The other person-
But you know what? Life isn't fair. And they turned out pretty good looking, if I do say so myself. And I do.